All right. Let's start a recording.
Okay, so as I've reiterated tons of times, but I'll say it again for the video. And are you streaming on Discord or?
Again.
No, I mean it's fine if you're not. I'm just curious if everybody was online. This will be an introduction to the language and formal notation that we'll be using in the remaining lectures in this series. And this series, of course, concerns itself with Poisson geometry, as I've drawn so aptly on the board. So I always like to start off my math talks by stating that my formal background is actually in physics. And so our motivation for this and my interest actually lies originally in physics. And particularly, we are interested in the mechanics or the motions of particles. And from that, we always have some position of a particle. So this is like the main motivation. We'll call this, we call it Q or P?
Q.
P is momentum, Q is position, right? Yeah.
Yep.
And momentum P. I should have started earlier with like a slight little historical background. Poisson, the guy credited with this idea, or with the origin of this bracket, is started out by studying the motions of particles. And then it turns out that Jacobi and Lee found out that this bracket structure appears in many places. Jacobi found that giving it extra structure creates a whole new area of mathematics, and Lee used that new structure to study DEs. So that's fairly interesting. Anyway, going back to this. And with the position and momentum of a specific particle, we have some associated quantities. These quantities being the kinetic energy and the potential. And the potential energy, what is it, T? Is it always T? Yeah. Is P squared over 2m. Is that true?
Yep.
Yeah, it's true. And the potential, U, is just some function of the position. And with these two quantities, we create the Hamiltonian. And the Hamiltonian, normally just denoted as T plus U, so directly as P squared over 2m plus V of Q. Without going into too much detail as to how to derive the following quantities, Hamilton ended up using this formulation, finding out Hamilton's equations. Lovely name. And he found that Q is P over M, which is equal to partial of the Hamiltonian with respect to P, and P dot, which is the force, is equal to negative the gradient of the potential, as we all know. And this, with respect to that equation, is simply the derivative of the Hamiltonian with respect to Q. And so this is all nice, and this is specifically stuff that we've seen in classical mechanics. But what if we have some other function of interest, which is dependent on our position and momentum, P and Q? Well, we know from multivariable calculus that the derivative of such a function by the chain rule is simply partial of f with respect to q dot plus partial of f with respect to p dot. Using Hamilton's equations, we could plug this in. So q dot for us is partial of h partial p, and then p dot, if we plug it in there, we get partial of partial h, partial q. Too many p's and q's floating around. And this should look familiar to all you guys, especially if you're taking a class on quantum mechanics, because this form here is the canonical definition of the Poisson bracket, and it appears so often that this is the bracket between f and h. So f dot with respect to this Hamiltonian, of course. It should be noted that, we'll see later on that you can associate different brackets to different actions. And this is sort of the beginning of our journey. So let's talk about it more explicitly. Is there anything I want to talk about before? Nope. This is actually, I should change this. This is the, how do I do this? This is defined to be the Poisson bracket. The canonical Poisson bracket on r to the 2n, to be more precise.
You want the defined to be on the other side?
Yeah, is it the other side? Yeah.
Or you would have thought.
Yeah.
Wait, you mean on this side?
Yeah.
Yeah. Thank you. Yeah. We'll see more clearly when we talk about Hamiltonian flows, if I get to that, about how we can generalize this idea. But let's first talk about it explicitly on a manifold. A Poisson manifold is a pair M endowed with a bracket such that, HRB is a manifold M endowed with a bracket. Manifold M endowed with a bracket, curly bracket, such that, one, it is skew symmetric. So for all, yeah, so this is interesting. I think I want to state right now that it's defined on smooth functions. So it takes in two smooth functions and outputs a smooth function. However, in my next lecture, I want to talk about the complex structure, and we actually replace these with holomorphic sheaves. Way out of scope for this lecture, but we'll get to that because these functions don't necessarily have to be smooth. Anyway, it's skew symmetric, so for all f and g in C infinity M, it satisfies this. The second property, which I'm sure you guys have all seen before in your quantum mechanics classes, is that it satisfies the Jacobi identity, which I'll write out now, but for the remaining of the lecture, it's not a plus. Hold on. It is a plus. G. No, it isn't plus.
I think it alternates between plus and minus
Yeah, it's plus and then minus, something like that.
because of the Levitch-video.
Well,
If it's the same as the lead bracket, then it should all be plus.
it should all be plus.
If you just permute it, it should be just plus. Yeah.
Okay. H 0. And then our third and final and most interesting is that it's actually a biderivation, specifically, but it is a derivation in both arguments. So it's Leibniz. Is Leibniz in both arguments? And this third one is particularly interesting because we are taught in basic differential geometry that, or does someone want to tell me what being Leibniz gives us? Other than you, mostly pointing towards you, because you just took the diff geo class. Do you know?
2 years.
Any ideas? Okay, go you want to say it.
Product rule.
I know, that's what Leibniz is. Gives us a vector field. Gives us a derivation. And we know that derivations define vector fields. The vector fields have a basis of derivations are a basis for vector fields. Is that what it is? Yeah. Always good. Yes, isomorphic.
The space of directions at every point is as significant as the space of derivation.
Okay. Okay. So it's a derivation, so it defines a vector field. And I'll skip over the Hamiltonian vector field for now because I just realized in my next talk, so we don't really talk about that. But if we want, there's a specific vector field called the Hamiltonian vector field, which will come up. So this specific vector field, because it's a derivation, so it defines a vector field. We'll get into mathematically what that means. Is special. It's so special. It's H M. Yeah. It's such a cool. Is the Hamiltonian. But this isn't really important. It is slightly important if I want to talk about orbits and then how to classify orbits, but I'm not going to talk about that, so this isn't really much importance for us. But we want to talk about this thing locally, and actually it turns out that this bracket is fully determined locally. But what does this mean? Well, we want to talk about for functions on open subsets of our manifold. We could talk about the bracket defined locally as simply the bracket on the functions described locally. So yeah, nothing particularly crazy, but this is really important to us because we can determine if we wanted to know things about this bracket, or more specifically about the structure with which the bracket is endowed on, we can just look at these things locally. And from this, we have, if we have a local chart U, which we'll just say is defined as defined with the coordinates x1 up to xm, the Poisson bracket takes the form for smooth functions. I'll use pi here, and you'll see why in just a bit. No, maybe. I don't know actually. But we use pi for the bivector, which uniquely defines the bracket, which we'll get into that in a second. For some is it clear why we get this, or should I go through it? Anymore? You probably heard it. Should I go through it? I'm going to go through it. I know you're lying. So just as an aside, coefficients, if we were to write a vector field, so we could write a vector field some x acting on the coordinates down to the partial. You've seen this in your differential geometry class. And this is why I think it is a basis. The partials define, yeah, the partials define a basis for vector fields, yeah. With these as their coefficients. It's a fairly easy proof. And by Leibniz, it's quite easy to see, show that you get f x q x f So in fact, this implies that xf itself is a derivation, and we can write it as some functions. J. And then we saw that applying f is just the derivative, so you just put in g, and you get your. Yeah, it's. Is that? Okay. Take my word for the thing. Lol. Okay. Yeah. There's something fairly important that happens in the bracket, which I guess we will get into not this lecture, but in the next. Just something called a Casimir function. Or an element, sorry. Defined as some f c in a smooth function such that c f is equal to 0 for all f. So this is particularly important, not for anything that we'll see today, but that will come up. And it's basically just a function which annihilates every other function with respect to this bracket. Any questions so far?
So like bracket is kind of like a linear transformation from functions to derivation, and the Casimir elements kind of form.
Yes. Yeah. Naturally, did I actually? Yeah, so here, a Poisson manifold is a pair M with bracket, and I'll denote this as this pair here. So, a Poisson map,
They do that.
Yeah.
If you take the bracket, if like locally you consider the coordinate function,
Yeah.
you take the bracket of that, or you take the partial derivative from that coordinate system.
If you take the,
Like if you just have some local neighborhood with some coordinates, you take like the coordinate function xi. Is taking bracket of xi
that just gives you these.
partial by partial xi, or it gives you pi?
Yeah, it gives me the pi's back. If I bracket if I do like xi, xj, is this what you get pi ij? You
Like
pick up
if
the
you put, if you plug in f for xj, you get like del xi of f. Like in your bracket, if you just take the bracket of xi with f, you get the partial of f with respect to xi.
Yes, yeah. Sorry. Yes, that's true. If I do this, because you're picking out the individual term. Because this, if I do like xk or whatever, you just get the kth derivative of f. Times this constant function. Because it'll pick up the Kronecker, which Daniel so aptly argued that it is a map on smooth functions. I don't believe it either. And Jason Bell also doesn't agree with you. Because I asked him. For the record, it is not a map on smooth functions. So if we have two pairs, a Poisson map is a smooth map. A Poisson map between is a smooth algebra that right? Yeah. So what do I mean by that? It means if I take the bracket, so if I get this right. Is a smooth natural homomorphism. What do I mean by that? I mean for any f, I'll write it out. F composed with g composed with phi on 1 is equal to the bracket of f and g. 2 these are elements on. Make sense? Yeah.
It's not really a Lie algebra.
Is it just an
It's a Poisson algebra.
Just-
The Lie algebra is it's a Lie bracket. Oh wait, am I dumb? Yeah, that's calling it a Lie algebra, isn't it?
yeah?
Yeah, okay. My mistake. Yeah,
Oh.
sure.
The first 2 points give us that it's a Lie algebra.
This is just
Yeah, I mean, I guess if we want to be like uber specific, because of that third point, we do get that it is like we can call it a Poisson algebra homomorphism if we wanted to, because these still have to respect the third point, which is a derivation.
Phi is actually a map between the map.
Yes, between the manifolds, yeah. However, I just always want to make it clear that the manifolds do not need to have the same structure. What else? And then a Poisson diffeomorphism, anybody want to guess, is a Poisson map which is also a, yeah, which is, yeah, also a, yeah, just a diffeomorphism. It's a Poisson map, which is a diffeomorphism. Okay, let's see, do you want to talk about that? Sure. This won't come up again, but another thing that pops up on manifolds is vector fields, and we actually have a notion of that. A Poisson vector field I promise it gets a little bit more interesting afterwards, after the examples. A Poisson vector field. That's fine. So it kind of has this product rule structure on it. Plus F. This doesn't really pop up again, but it kind of has, because we have that notion that vector fields are kind of like product rules. So, or not are kind of, they are product rules. So we have a notion of a product rule with some vector fields. Okay. Let me go through an example. Okay. So sorry, by the way, that I haven't like memorized my notes. I only wrote these out the other day. So hope it's okay that I'm looking down at my pages all the time. Hopefully for the next one it won't be the case. So let's consider the map from sending the coordinates qi to pi minus Yeah, it kind of looks a little funky, but this is the standard Poisson, or the standard bracket on. Oh no, I'll go through the standard bracket. The standard bracket on R to the 2m is the one that we see all the time in quantum mechanics. Um, and then the standard bracket, which we define. Now, these are only examples of brackets. And this is the exact same one we saw earlier. And these AIJs are actually from a fixed choice of a skew-symmetric matrix. But yeah, we can choose it. It's not skew-symmetric. And so if we recall the definition of a Poisson map, we have to check certain things. Namely, we have to check, not certain things, just one thing. Where's the eraser? We just have to check that that property is satisfied. It's fairly easy. And actually, I'll just ask you right now, before I ask if it's a Poisson map, you guys think that it's a Poisson differential? What can you tell me immediately? Not you really. Umar, what do you think?
I have no clue.
Chris? Is it a Poisson differential? That would say there's no way. Yeah, so it's not. So the first thing we notice immediately is that truly this is true, but what do I mean by that? I mean, oh yeah. I mean, I'm just taking the derivative of this guy with respect to pk and the derivative of q. And I recover these two quantities. And what that allows me to do is check. The other thing is, remember I talked about how it's innately a local thing, this bracket. So we actually only need to check it on local variables. So to check this property, we need only check that it satisfies locally. And so locally, for any functions, f and g, phi composed of fg will just pick up the some coordinates, some local coordinates. And then using these two properties, we immediately get, but the sum over the Dirac deltas end up collapsing into what is a, j, xi, j minus, j, and oh, yeah, it's skew-symmetric. So transpose is equal to negative. So we can swap these, pick up a plus sign, and we get, well, I'll show you in a second with this guy. J, because it's skew symmetric, you can swap these, pick up the plus sign, and then cover it J. This one and then you just cover. So because I have locally an R to the 2 and then this just picks up the bracket on R to the n if I take it with the basis. Just pick up these components. So the base, it sends basis to basis, or basis to basis. Locally speaking, the coordinates on this guy get sent to the respective here. It gets sent to this guy. So fine and well. Yeah, and is it a Poisson diffeomorphism? No, it isn't. So this is all nice, but there's another way that we can look at the bracket. And the way we do this is actually by looking at polyvector fields. Now, in 465, smooth manifolds, or your differential geometry class, you learn how derivations are uniquely determine vector fields. However, for us, we are not working with a two-dimensional vector field. We're actually working with a three-dimensional one, trivector field. And to do this, we actually want to talk quite a bit about Poisson bivectors. So a Poisson bivector, before we look directly at Poisson bivectors, we can recall the form that we had written the bracket in before. We had written it as the sum of smooth functions, partial, with respect to our basis, blah, 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 blah. And there's another way that we can look at this. Namely, we can automatically pick up skew symmetry by, or let me write it first. J for some smooth sections on the tangent bundle. We could just look at them being on the tangent bundle if you specifically want smooth, but this isn't actually a requirement. You can also define it without it. And this thing automatically picks up the skew symmetry of the bracket, and everything else also follows. It's easy to check. So we know that it, yeah.
I have a question about why IIJ should be a section of the is the wedge between the two derivations? Well, the wedge between the two derivations is like a section of the tensor product of two copies of the tangent number. Now we have another two exterior forms. Yeah, why should the pi ij take in vector fields and not just points?
Oh, is it?
So you're saying pi should be that? It's
Yeah,
not pi,
it should
right?
be this, I think.
Yeah.
That makes sense.
Yeah.
Because that's returning components.
Yep.
Yeah.
Yeah.
There you go.
Yeah, good. Yeah. And we'll see this more clearly later, but there's a cookie side. If you remember your multi-linear algebra, We do.
So wait, I'm so confused. But doesn't
Yeah.
that expression really make sense locally? If you have a local chart with xi's, how does it make sense to piece it together locally?
Sorry, what's your question?
So your pi that you wrote down to sum over these del by del xi,
Yeah.
del square by del j, those terms are only defined in the chart.
Yes.
So how are the chart-wise definitions getting stitched together to make a global section?
Shiftification.
How are your transition functions?
Well, hold on. Why are we talking global? Because of this guy?
Section of the
Yeah. Yeah, because I want to talk about it inherently locally. So maybe I just remove this line to remove all the confusion.
There might be a way that that's pieced together.
There is. This is called Darboux. This is like an actual thing. And always write it like this, but I don't have an answer for you right now.
Can I get away by answering your question by saying sheafify this pre-sheaf? No.
Because you have to verify that restricting from two different things
Gives you the same thing.
That's
Right.
essentially what I'm asking.
I mean, you can probably prove it.
Yeah, but it sounds like it's hard. So
Yeah, I mean, yeah. If you look up, I forget. It's like Darboux something theorem, or Darboux not splitting. It might just be Darboux theorem. That you can write it. You can write it like this. Yeah.
Can I ask about that?
Yeah.
Can you explain to me the indices that in the first line for both expressions? Because the index notation that physicists use, for the first one, the delta. Um, how do you have two i's? You're not summing over the i's, right?
No, I'm summing over the K's.
Summing over the k's. Okay, but then so on the left hand side you have a k dependence, right? P because of pk. On the right hand side there's a k dependence, and it looks like you're summing over the i's. So basically, what I'm saying is mismatch indices.
Yeah, probably.
It's not a huge deal, but
Whipped up this question last night. So there could be something wrong with the indices, probably.
I checked
But the idea is it's fairly simple. Like regardless of the indices, these guys will just pick out the components or the matrix components, and you swap them because of this delta. Regardless of what these indices are, the delta will swap these indices, the ji rather than ij, and then everything follows from there.
the rest of the indices, the other lines, is all
this
correct.
is probably wrong, and I don't really care too much.
Yeah, but they're correct. The other lines, the indices, they match up. It's just the first one.
Okay, so a vector field can be identified with a derivation and similarly, a multi-vector field can be identified with this guy, which takes in, so a multi-vector field, let's see, how do I write this? Multi-vector field, we'll call it V. We'll denote it like this. Is identified with, so it takes in k functions. It's a function, smooth function, of course. Ooh, that's a cool little infinity sign right here. And it's component-wise evaluation. So it takes in functions f1 to fk, and we simply define it as E vector field. And so, similarly to how we saw in smooth manifolds, the vector fields are identified with derivations. So similarly, a multi-vector field is identified with what do we call it, multi-derivations? Yeah, well.
So is that notation? So you've taken tensor product of k vector fields and you're plugging in k different
Which one?
the v of df1 and v of k.
Like this guy.
Yeah.
This, we get a function.
What does it mean? What is that notation for?
Push forward. Or
Taking k,
Yeah,
taking k functions, you've taken their differentials, so those are all one form.
exactly.
Now, what are you doing? Are you evaluating those all on the k different components of your k vector field and multiplying them? What is this object? If I give you a point, what would you tell me is the answer? It's the number that it spits out.
well, it gives me the. Well, it's not a number. It is a
You're saying-
number.
you're saying
Yeah,
it's
yeah,
a
no,
function.
it's the. Well, it's just the function evaluated at that point along the vector field.
So if I come along with a p in your manifold,
Mm-hmm.
what is v of df equal to dfk evaluated at p?
Well, now in this case, it wouldn't be just a singular number; it'd be a whole like vector of numbers.
It should just be one number because you're saying that LV is spitting out a single function.
Oh,
Yeah, the only problem is just because there's multiple one forms there. But,
Yeah. So there's just as many one forms as there are like pieces of the vector field. So I'm wondering, do you just evaluate the one forms on the pieces
On
of the
the
vector
p-
fields?
I think the most sorry.
So like you just have like k vector for one forms and k vector fields, and you just evaluate and multiply together.
I think that might be the most natural. Because if it was one, it's just a vector space is a map from a one form to the field. As you know.
Yeah. Okay. Okay.
yeah, but okay. I don't know why multiplying those is the most natural.
Because it's
Sure, but I
bilinear.
could do.
Tensor
Addition.
product is a multilinear thing, and so is multiplication. So like
Yeah,
tensor
okay,
product is
okay.
something that's weighting to multiply.
Yeah.
against it.
But you can also add, right?
Yeah.
Add the one forms, get a single
You
one
have, like,
form.
You have the wrong
Right.
doesn't behave the same way as tensor product.
Yeah.
But multiplying it.
Okay. Yeah. Okay.
I think, yeah, you can move on.
Yeah, I'll look into it afterwards. Again, super scuffed because I only have like a day. But no excuse. I'll look into it. I'll send it later too. I'll send you the notes that I followed or that I was reading to learn this stuff.
Yeah, just got confused because I'm not like a big deal.
Yeah.
What does that mean?
So we have a one-to-one correspondence, just like we did in the one-dimensional or the just with the vector field, multi-vector fields. Corresponding with alternating multi-derivations. And, the alternating, I guess we'll see that in a second, because we have the regular notion. Okay, regular vehicle. Okay, yeah. Okay. We'll see the alternating in a second. So, as we saw, the bracket was a bi-derivation, and so we should have a, so bi-derivation. The math. Taking in two functions, spitting out another. And so it has a corresponding, which is R linear, skew symmetric, and Leibniz, which is almost a Poisson bracket. It's almost exactly what we need. Is skew, it's R linear, skew sim, and Leibniz. But we don't know yet if it's Jacobi. And to determine the analogous version of the Jacobi identity using these bivectors, or using this new formulation of multi-vector fields and multi-derivations, we have to now look at, I guess we need a new formulation of this identity. And for this, we need something called the Skoughton bracket, which is a new bracket which now works similarly to a regular Lie bracket, but just in higher dimensions. So for a regular vector field, we know that the Lie bracket, the Lie derivative satisfies the following identity. And for multi-vector fields, we define the Skoughton bracket to be the unique bracket, so multi-vector fields. Define for V is a K vector field, and W is an L vector field, and the Skoughton bracket, which takes in two of these and spits out is the unique multi-vector field, this product here, this product is the unique multi-vector field satisfying, how do I differentiate this? Maybe I'll go like this. X W. It's almost the exact same, but now you have, it's in a sense like braided. Oh. And there's a definition for what these guys are actually doing in the multi-derivations, but it's the exact same thing except you sum over all possible permutations of the entries up to signs. I'm not going to write it out because it's long and tedious, but it's just you sum over all possible shuffles of the indices. So for a biderivation,
question. Or I guess comment, I don't know. If V over there, if it's a kth vector, as in like the wedge of just normal vector field, then it'll take, if you imagine the combos between the one forms as wedges, it takes in a K form and spits out a C form.
Oh, is that what it was?
I think that's
of the forms?
I think that's what it is. I think V is in XK. I don't know. What do you call it? And it can take a K form and spit out a number.
Yeah.
and the operation, the commas between those one forms and the input are wedges.
Wedges. Like
I think
between
that's
all of them.
I think that's what it is.
Okay. So maybe I wrote that down wrong. Who knows? Or maybe it's like implied. Maybe.
Yeah, I think it's. Oh, actually, you did write v. V, you wrote x to the k. Yeah, you wrote it there.
Yeah.
Yeah, it's just the operation. I think is wedges.
Okay. All right. Glad we got that cleared up. So for a biderivation, uh, with associated bivector field, pi. We could maybe I didn't write it down. Now that I'm thinking, I should have. But you can actually show that the this h is actually equal to. I'm just going to write out jack of this. Okay? H, but this is the cyclic permutations of the bracket. And so specifically, what we get is that on any manifold M, so this, any manifold M, bracket, which is simply the contraction of pi into EF to G, gives us or induces a one-to-one correspondence between brackets on M and bivector fields satisfying that pi bracket pi under the scout bracket is 0. And actually, Chris, this is why I asked you about overdetermined PDEs, because this thing actually gives you an overdetermined PDE, which is quite nice, and apparently you can do a lot of cool stuff with that. But I didn't read into it too much.
Can you write down the name of this item?
Yeah, scouting, which is spelled really weirdly. Please comment if you know how to say this. I thought it was shooting or shouting, but apparently it's scouting. Scouting. I don't know.
Yeah.
Yeah.
It's like Maddie's last name.
Schultz.
It's Shoots, but like the American version, I guess, is like Scoots or something.
Yeah.
I don't know.
Okay, so the next thing that we can talk about is so we talked about how we can represent the Poisson bracket as, which is a biderivation, as the bivector field pi under the Scout bracket. But there's actually another way you can do this with musical isomorphisms. In light of not wanting to be absolutely viciously mauled by you two, I'm going to refrain because I genuinely don't think I know that part enough. However, just as like a little hint, or just a little taste of it, where did I put that? As a little taste of it, you can define with the musical isomorphism the exact same picture. You have this sort of new derivative, you have this sort of new thing, you write everything in terms of contractions and whatnot, and you just get like new Lie derivatives, new brackets, and the exact same thing. You just get that, if the bracket satisfies Jacobi, or if the associated bracket allows you to satisfy Jacobi, you get that it's a Poisson bracket. There's also another interesting thing which I didn't mention, which I might want to mention for later, is that Poisson structures also induce a one-to-one correspondence on the dual space, which is kind of cool. Should probably mention that, but it goes into a little bit of Lie algebra. Lie William, maybe you've heard it with Daniel as well, the moment maps. But yeah, there's like a unique moment map associated on these manifolds. So maybe I talk about that next time. But I wanted to move into now the deformation stuff. Hopefully, so now whenever I talk about like Poisson structures, I might just say that we have a manifold M equipped with a bivector field pi. And I'll denote it like M pi. And this sort of defines our Poisson structure. There's cool things that come out of this. One of the things is the classification of Poisson manifolds. Maybe you guys have heard about all these sort of problems. Certain manifolds equipped with certain structures can be classified, as we all know. And the classification of Poisson manifolds is actually an open problem. One of the big ones, Fano manifolds. If anybody knows, it has to do. Fano manifolds are like higher dimensional manifolds with specific rank conditions on their. I don't know how to speak to it. But the problem of classifying Poisson structures on Fano manifolds is an open problem called Bondal's conjecture, which is pretty cool. At least I find it cool.
Is there like a condition that says that a manifold doesn't have a Poisson structure? Or is there always some?
Actually, so yeah, that's really cool. Poincaré's lemma tells you that you will always have one, actually. But you'll only have it on symplectic manifolds. That only gives you the absolute existence of Poisson structures on symplectic manifolds. But I do not know. That's why, again, in the higher dimensions, it gets a little bit trickier because the classification problem also says, do we have a Poisson structure on these manifolds? And it turns out, which is what I'm going to talk about, deformed manifolds always have Poisson structure. Because in the deformation process, which we'll see here, the linear term is Poisson bracket. If you have a commutative, I don't want to say algebra, but I will say for now, I might be wrong here. If you have a commutative algebra with a commutative product, and you deform that product into something perhaps non-commutative, actually most of the time non-commutative, that non-commutativeness is captured in that Poisson bracket in its linear term. And we'll get to that right now. And this was proved in the 90s, actually. Every deformed algebra has a Poisson structure. But yeah, I can't speak to just manifolds itself, if that's what you were wondering.
So like, you would be able to say, here's an example of a manifold that does not have a Poisson structure. Disorientability, is that necessary?
Oh, good question. I'll get back to you on that one. I know that you could always... Oh, that's actually not true. You can always equip it with the trivial bracket, which sends everything to zero.
Zero counts?
Yeah, zero counts as a Poisson structure. It satisfies all the axioms. So, yeah. So, yeah, technically, it's trivially true. Kind of funnily enough.
You have to have some global condition you want to satisfy in order to find it. But it doesn't work.
Yeah. Yeah, that's a good question. I'll look into that for you. I wrote down here a little blurb. Poisson geometry is also closely related to deformation theory, as we can consider deforming the product or commutative product on smooth functions to possibly non-commutative products, which encode the Poisson bracket. I'll show that now. So our interest now in deformation theory, family of products. Possibly non-commutative F. So these products depend smoothly on H, such that as I take H to 0, we recover the original commutative product on our algebra. I'll write this on a little bit clearly. As 1 is unit, and F0G is the regular pointwise commutative product. Regular point was bottom. Here. And the commutation, the other condition that we impose is that the commutation vanishes the first order. In H bar. Specifically, we require that the bracket is the linear term in this commutation. Minus G. So if this kind of doesn't convince you right away, I mean, this just means that the I might write it like this. I'm lazy. Fg with respect to h bar, but that's just a product of f and g with respect to dot h is equal to h times bracket plus higher order terms h bar. William, you have a question? Okay. Yeah. I mean, this is just the general picture. We go more. Sorry, no. This is the specific example with the Poisson bracket, but we'll go more specific actually later on. Let's see. Yeah. So now let's be precise. An associative R algebra, or a formal deformation on A is an algebra structure. Star, i.e. the product is defined, we'll use star, on the formal power series in H bar such that the product is R H linear in both arguments, and the isomorphism is an isomorphism of algebra, so it preserves the structure, the algebraic structure. And that the structure preserved. And star is uniquely determined on its action A, namely for A, B in our algebra, A star B the product plus all these extra terms. 1 E squared 2 E and so on and so forth. And a formal deformation of any algebra, if we use this idea over here, gives us a Poisson bracket defined uniquely by the difference of F1AB minus F1BA. To see this more clearly, it's not difficult to see because if we consider the idea again of the commutation of the two elements, you'll get AB under the commutative. So this product is the commutative product of our algebra.
You don't actually explicitly say that it's commutative. So
Sure. Commutative too. We always deform from a commutative to a non-commutative. Or actually possibly non-commutative. It can still deform into a commutative. However, the ones with the Poisson bracket end up becoming non-commutative. F1 E plus one minus PA minus H1 PA. All these terms cancel. We're just left with because we only care about the first order term. The other guys don't vanish, but there are higher order terms in this part. And the Poisson bracket is given by the linear term, so our Poisson bracket is given exactly by this difference here. Check that out. So, the following definition will be the last definition. The deformation quantization of a Poisson manifold is given by the star product on the smooth functions, equal smooth functions with such that this is, well, as we already said, one, this is a deformation. With star is a deformation of the algebra structure. Do you have your Mandarin thing?
Mainly because of
The algebraic structure on C and the M. Three functions on M. Two. The FIs are bi-differential operators in F and G or in both arguments. And three, the bracket is defined as the difference of the linear term. So, all that to say, whenever we have a quantization or a deformation of my algebra, the Poisson bracket is the linear term in deformation, and we can just encode that generally through this idea. Yeah.
So the definition of deformation on a Poisson manifold, it seems kind of like you just have a manifold.
Yeah.
You're endowing it with.
Yeah. Sorry, I got a little bit too ahead of myself thinking about the Poisson bracket. But yeah, it's deformation quantization of a manifold given by the star, such that the linear term is a Poisson bracket. And so the manifold gets deformed into something which has a Poisson structure on it. So
Depending on what you're
yeah.
Poisson bracket.
Yeah, could be. Yeah. The other thing is, the really, really famous one is the Moyal product. I'm sure you've heard of that one. I know you're doing it, but the Mayel product is the one we get in quantum mechanics.
Oh.
The IH bar, like how you get the commutation relation of the bracket is like, you get like FG, I'm going to sum it up, under the Mayel product, which is star, is equal to like IH bar, or negative IH bar. Someone correct me for quantum mechanics. But yeah, there's that term in front, that's that difference that you pick up in there. But yeah, it could be trivial. Yeah, it's actually, okay. I feel like I wasn't necessarily clear. I should probably, like,
I have a question. So for this board here, what does it mean, the first line, when we take the derivative of that
That's
with the
this.
product?
That's this.
I see. So it's defined as that.
Yeah. Let me just write this out.
And it's a
So the
definition.
linear term, yeah, it's a definition.
I see. And you just take.
Sorry, whoops. It's a definition.
Okay. Nice. And you just take normal derivatives and set it equal to 0. Okay.
Yep. Yeah.
Nice.
Yeah. And obviously, there cannot be a constant term because then everything will just be up to some constant. I guess you could take a constant term, but then all your operations, everything will just be up to some extra constant.
Sure. What's some of the basic axioms you would be satisfied with protecting
Extra constant.
Oh, like by linearity. So it'll be affine or Jacobi.
Like instead of being
Yeah, sure, but then you won't get a unique
Oh yeah,
bracket though.
yeah.
You won't get a unique bracket, I think. Yeah. Yeah, you're right. Everything would still be satisfied.
I said not that.
Oh, not satisfied?
Yeah, if you have like a random constant getting spit out every time you put a bracket. Then like
Oh, that's true. That's true. And then also it
Bilinear.
wouldn't necessarily be bilinear,
Exactly.
and it also wouldn't be skew symmetric.
Yeah. It'll be
Oh
affine.
no, it would be. It's the minus.
you get a constant when you change the sign. Like, switch
Yeah.
it into the brackets,
It wouldn't be skew symmetric. Yeah. So yeah, everything fails. Yeah. Yeah.
It'll be some affine thing.
Yeah. But we wouldn't really care about that. Okay. Any questions about anything? I think. And my next talk is on the 27th, so definitely more time to prepare for that. And
Sorry again.
no, it's fine. I just hope that it wasn't too awkward, just me staring at my notes all the time. I felt like it should be a little bit more appropriate to like know this stuff off the dome. However, we were looking at smooth functions, and in the next talk, I want to talk about holomorphic functions. And it turns out all this sort of Poisson structure carries over to the complex case quite well. And the classification, everything actually becomes like easier or trickier depending on how you look at it, because you can start talking about things a little bit more algebraically. You can use some algebraic geometry to show, specifically with the classification of manifolds, you end up just talking about the classification of elliptic curves, I think. Yeah. But I don't want to speak too much about the elliptic curve stuff, because I don't know too much about the elliptic curve. But we can sort of work around all of that. Yeah. Good. And then, as we said, I'm going to look into that, what they mean by the V of the DF, but it makes sense to be,
Yeah, I thought like the x to the k thing was like k tensor powers, but that's k wedge powers.
Yeah, it's K wedge powers.
Yeah.
Yeah, it's K wedge powers. That's why I was kind of confused when you started tossing the tensor product, but
Yeah.
I sort of ran with it. I should have mentioned something, but
Yeah, it makes more sense though if you just have k wedge of k forms and a wedge of k vector fields and you go chomp and you get a number.
yeah.
If that doesn't work, when in doubt, do it pointwise.
Yeah, I mean, that when you asked that question, I just thought, yeah, you can just do it point-wise and just call it a day. But, yeah.
I was gonna say something about the holomorphic properties. I forgot. Because you get certain nice things when you do it in the smooth category that it doesn't generalize for the holomorphic one.
Yeah, and we actually don't work in the smooth category. all the interesting stuff comes from the singularity stuff.
Right.
Yeah.
Right.
So
Yeah.
that's what I want to talk about. Like, you're gonna have to start talking about sheets and stuff like
Yeah,
that.
exactly.
So I mean, it's actually fine because then you just define the bracket as just takes in two holomorphic functions. Whoops. Oh, it spits out another holomorphic function. So yeah, you can just reformulate everything with sheaves, but nothing really changes fundamentally.
Yeah.
The only thing is like degeneracy loci might be more interesting, but that's where you get the elliptic curve stuff. The degeneracy loci of Poisson brackets, I think there's like 5 or something. So I thought so too, and then I got corrected, and I embarrassed in front of everybody. My algebraic geometry prop. So I don't know. I thought because locus, plural is loci, and she kept on saying like loci, and I'm
focus.
yeah, and yeah. So I'm like, oh, like loci. When you say loci, you mean like the degeneracy loci, like the zero. She's like, no, loci. I'm like, oh, okay. So yeah.
I'm gonna look at the dictionary when I go.
I know, I didn't believe it either, and I hate it, because now every time I look at a lecture online, they're always saying loci, and I'm like, why? Yeah. But yeah, the degeneracy loci are classified into 1, 2, 3, 4. 1, 2, 3. Yeah, there's 1. Is it 5? Is it 5? Might be 5. All the degeneracy loci of the Poisson brackets get classified into these 5. And the way you actually find this is you talk about how you can like blow up points on Poisson manifolds, blow up and blow down, and so you can create like a whole. You can just infinitely create more and more by just well, not infinite. I don't know if it's infinite. You might have to correct me on that, or I might need to look into that. But for any Poisson manifold, you can always just blow up a point to create another one. And the exceptional curves that you get when you blow up those points, do you know what exceptional curve is? Yeah, it's like when you blow up a point, you consider all the lines through it, except when you blow it up, you get this exceptional curve, which is like all these points sort of, like the manifold ends up looking like all these. So on our original manifold, I might mess this up too, but you take a point, you consider all the curves through it, you blow that picture up, and you get a new manifold, which looks like this, like all these curves through it, and then this is your exceptional curve. And the exceptional curve is defined from elliptic curves. And the exceptional curves can take is that right? I really don't want to speak on it because I fear I don't know. But I'm pretty sure this exceptional curve that you get when you do the blow up operation, the degeneracy loci, this one gets classified into 3 possible points. Yeah, I have to, let me, I'll send you something. Let me think about or look into it a little more.
What does it mean to blow up in this case?
Like take a manifold. I want to create a manifold from another one. And so what I do is I take a point on the manifold. There's an actual formulation of the operation that I'll write down next time, or I can send you in the Discord. But you look at all the curves through that point, all possible curves laying on the manifold through that point, and then you essentially take that collection of curves to be your new manifold. You kind of just look at those curves as your new manifold.
And then just connect some with complex projectors.
Yeah.
You connect, what was the first one?
You connect some with complex projector space, because that's your space of all lines.
Mm-hmm. Yeah, CP comes up.
CP1?
It
depends on the dimension of the manifold.
And you just connect them all of those projectors?
You have like a singularity or whatever. You cut out a little nicely disc around it.
Is this related to the index theory stuff that you were telling me in rational homotopy theory?
No, it's more related to Kirby calculus.
Wow. Things I've never heard before. I know you like tossing up index theory. But, yeah. I feel like that's a good place to stop.
and then